Okay, we're going to continue on here, chapter 2. So with the holiday, we'll try to catch up a little bit. So last time we got into, obviously, measurements there at the end. And again, a reminder that when we do take a measurement, um, there's always some type of uncertainty associated with a measurement. So as we talked about, when you are taking any type of measurement, be it a ruler, be it from a graduated cylinder, anything that has basically a scale on it, we want to always take a look at that scale. And as we talked about, we really want to look at the two types of markings that you typically find on these scales. One, again, is the larger marking. And as we saw last time, when we look at the sort of larger markings, those typically will actually have numbers next to them. So they are pretty well defined. And the difference between the large markings here, again, is our 10 milliliters. At that point, we want to look at the smaller markings, which basically make up the difference between those large markings. And we really want to count how many we got going on. So here, if I didn't mess up, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And in that case, we have 10 markings from a difference of 10 milliliters. That tells us in this case that each of our smaller markings is 1 milliliter. This again being 11, 12, 13, 14, 15, 16, 17, 18, and 19 if I squeeze it in. Once again, we take a reading of something. There are always going to be certain numbers that no matter who looks at it, everybody should agree. So for example, here, if we look at it, everybody should agree it is at least 13 there, my bad, 13. But everybody should agree is at least 13. And that is when we take a measurement, usually referred to as all of our certain numbers. And again, we want to always record all the certain numbers when we take a measurement. These really should be all the numbers that nobody disagrees about, and everybody sort of agrees. So what's left is sort of that estimation or the uncertainty in the measurement. And again, depending on sort of how you look at it, you may feel it's halfway there between those two numbers. You may feel it's not, but you do need to, in this case, go one more digit over from the smallest marking. And that is what is referred to as our first uncertain number. And with that first uncertain number, that is what we want to record, obviously, with our units. When we do that, as we talked about last time at the end there, that is significant figures, basically. And this guy would have 3 significant figures in this particular case, with the uncertainty lying there in the last. I'm sorry, say your question again one more time. It should be basically what we talked about, that you could figure out how far you could take the reading, for example, usually one more place to the right of the smallest marking. When they talk about usually tolerance and stuff like that, or sort of uncertainty, that's sort of what we talked about when you can take the smallest marking divided by 2. And in this case, you'll get plus or minus 0.5 milliliters. And that is basically how far you could take it to in this particular example, which is the first decimal place in this case. So that's usually what it means. So usually when they talk about sort of taking the reading to the tolerance, it's really a fancy way of saying, give the reading to the proper number of significant figures, how far you can kind of take it to. So you wouldn't want, in this case, to answer your question, you wouldn't want to record 14 milliliters for this measurement. That's because 14 milliliters here would have only 2 significant figures, right? Where you're saying the uncertainty here is actually here in the second digit here. And that means, again, what this would mean is it could be like 14, could be 15, could be 13. And once again, we can see that we're right about there. Based on this equipment, we could actually do much better than that rounded sort of measurement, and we should do much better. We could actually say that, I think it's 13.5, but maybe it's 13.6, 13.4. That is where the uncertainty is, and based on the scale, that is basically how far we can take the reading to. So again, if you do any type of rounding like that, you basically would make your measurement worse than it should be based on the scale that you have. Other questions? So always, those are really the two things that you want to figure out is on the scaling is the large markings, what they represent, the small markings, what they represent, and really how far you can take the reading to. Usually, as we talked about, is one more place to the right of the smallest marking. You definitely could take the smallest marking, divide it by 2, and you'll find the uncertainty or the tolerance in this sort of measurement. And as I mentioned, a lot of times at this school, when you're in lab and taking measurements, they do want you to kind of include that on your lab reports and stuff like that. Yeah.
Right on, say mark like a big number, let's say just
Yeah.
the uncertain number at all. Write down 10.
There is. So it depends on the scale. So for example, we take the same guy. Let's just say we were at 10 down here, right on this thing, right? So if we were right on 10 in this case, because of the scaling that's here, you can take it to the first decimal place. And you do need to record, in this case, 10.0 milliliters. Once again, when we look at this recording here, this would have how many significant figures? This would have 3 significant figures, right? And the uncertainty in this measurement is actually, right, this 0 right here. Now, if we did actually what you asked, which is if you recorded 10, for example, if we recorded 10 like I wrote it right there, how many significant figures would it have? Actually, in this case, it actually only have 1 the way I wrote it. It'd actually just be that one right there. If I wrote this, it would actually have 2 significant figures in this case. Now, in either case, if you wrote it like I first one I did, the uncertainty actually would be right there with the 1. And you'd basically be saying, I think it's 10, but it could be 20 or it could be 0. Which clearly looking at that scale is nowhere near any of those numbers, right? So now you just inputted a bunch of and uncertainty in this measurement that should not be there. If you did this one and you at least put the decimal there, the uncertain number would be the 0 in this case. And you're saying, I think it's 10, but it could be 11 or 9. Again, a little less error there, but still more error than you should have based on this equipment. And that's why, again, even if you hit, as I think we talked about perhaps last time, even if you hit exactly on the nose on a measurement, you always need to take it to the proper number of digits based on the scaling. And that may require you to insert a 0 to sort of maintain how far that you need to go. Other questions? Other questions on that? And again, that is a very very common error that people make when they're taking measurements is, they just go, well, it's like right on the nose there, so I'm just going to record whatever that big number is. Probably for a lot of times because they're like, I'm for sure it's on there. I can see that number, so that seems like a right number to record. But it's not just always the number. You got to make sure you do take it to those proper digits. All right, then let's continue on here as we obviously we're talking. As I mentioned before, it is custom to always record that first uncertain number along with all the certain numbers. And that's really going to give you the proper number of significant figures for your measurements. And again, the uncertainty lies in that last significant figure. So that's also a really important thing to remember, which is the uncertainty in the measurement when you look at a number does not always has to be the last number that's written. It is a lot of times the last number written, maybe about 99% of the time it's that last number that's written. But it will not always be the last number that's written where the uncertainty or estimation is, but it will always be the last significant figure that's written. So when you're looking at the number, you determine how many significant figures that number has. The last significant figure that's written is where the uncertainty lies. Now, again, confusing to a lot of people is, in a lot of cases, that is the last number that you actually see on the paper that's written, but it's not always the last number. So sometimes people go autopilot when they're asked a question like that, where's the uncertainty or what's the estimated digit? They always kind of automatically go to the last number, but it should always be the last significant figure that is written in that number. That brings us to accuracy and precision, and there is a difference between sort of accuracy and precision. Accuracy tells us how close our measurement is to like the true value. So if something is really accurate, then basically it will tell us that we are really close to what the true value should be. Now, if we have something that is precision or precise, what precision deals with is how precise a set of numbers are to themselves, or how close a group of numbers are to themselves. So when we look at something like accuracy versus precision, accuracy tells us, how good we were in terms of the right answer, if you want to think about it that way. Precision tells us how repeatable something is. So, for example, you can do something correct and be very accurate and also be very precise, or you can keep doing the wrong thing every time the same way and be very precise but not very accurate. So if you do something wrong but you do it over and over again the same way, you'll get kind of the same result, and that's very precise, but it may not be very accurate. So when we're doing something that is dealing with accuracy or precision, what we're looking for is both, really. We're really looking to be accurate and precise. We're looking to be able to get the right answer, and we're looking to be able to redo that experiment, for example, multiple times and get to the same answer at the end. So the classic example, as we'll see, is the bullseye type of deal when you're kind of throwing darts. And when you're throwing darts, you want to hit the bullseye in the middle. So if I threw some darts, for example, I hit here, missed the board, and hit over here. Am I accurate? No. Am I precise? I'm neither, really. I missed the board. Hopefully nobody was standing behind it, I hope. So I pick up my darts and I decide, all right, we'll go double or nothing here. Why not? We'll throw some darts, and I throw them, boom, boom, and boom. Am I accurate? I actually am not accurate, because the goal here is to hit the bullseye in the middle, right? Am I precise? I am very precise. I'm precisely not accurate, right? So again, as I mentioned a second ago, you could do something multiple times the exact same way, you'll get the same result, but the result may not be correct, right? So when we look at precision, what we're looking at is, how reproducible something is. And in terms of chemistry, a lot of times what we're looking at is like an experiment. That's why we do multiple trials of an experiment. We do the same experiment multiple times to try to get the same result, or see if we do get the same result. So I pick up my darts and kill my board here. And then I throw my darts one more time and I hit there. Am I accurate? Am I precise? Yeah. So usually if you're fairly accurate, you usually will be fairly precise usually. And that's really, again, the goal there is we want really both of those things. We want to kind of get the right answer, and we want to be able to redo that sort of experiment, for example, multiple times and achieve sort of the same result. Any questions on that? What are the things that help us look at accuracy versus precision when you get into experiments and stuff like that? A lot of times something known as percent error is something that is calculated to figure out how accurate you are. So usually you want a really low percent error. You have a really high percent error, that means not so good. You probably screwed up along the way. For precision, we look at a couple of things. Standard deviation, our percent standard deviation is something else that we look at. And standard deviation, again, is really a measurement that you do for all the numbers that you got and kind of compare them to each other. And that's what we kind of look at. So percent error is something that you come across a lot in chemistry. You use it a lot when you're doing experiments to figure out how good or bad, for example, you maybe did that experiment or didn't do that experiment. That's what we just talked about there. Agreement among the true value and precision, agreement among several measurements. And there again is our dartboard example. Guy on the left all over the place, so not precise, not accurate. Guy there in the middle, kind of precise. They're all kind of in the same area, but really, again, not on the bullseye, so precise, not accurate. And our guy there, dead bullseye, precise and accurate there. And again, that's sort of what we're looking for. All right, so why don't you take a moment here, and based on our ruler-ish, I think nothing moved, try to figure out what is the proper reading you should take here with this sort of uncertainty or tolerance there. So take a moment there and see what you come up with. And obviously these guys go to the big markings there. Okay, so let's take a look at, remember here, we again want to look at our scaling. So we can see our big markings there is basically 1 centimeter. Once again, we do want to count what we got going on in terms of our small markings. So remember that when we count those, we want to start past the last large marking. So in this case, we would start here, 1, 2, 3, 4, 5, 6, 7, 8, 9, and oops, try that again. I would try that again there. Try not to undo it again. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So again, our large marking was 1 centimeter. Our small marking going to be our 1 centimeter divided by 10. So that's going to give us 0.1 centimeters. So this would be 2.1, 2.2, 2.3, 2.4, 2.5. That would be 2.6, and right there would be 2.7. So in this particular case, we could see that it is at least 2.6. That is our certain numbers here when we do it. And again, in this case, it's not exactly 2.6, not exactly 2.7. It, to me, again, looks just a hair before the 2.7 marking. So it looks like 2.69 centimeters. This would be our first uncertain number. That would mean this number has how many significant figures? It has 3 significant figures. The uncertain number here is the 9. We once again can find our sort of tolerance or uncertainty by taking the smallest marking and dividing it by 2. That would give us plus or minus 0.05 centimeters. So that would give us a 2.69 centimeters plus or minus 0.05 centimeters. So that's looking like D would be a winner in that case. Yeah. Any questions? So clearly, this would have only 2 significant figures. So kind of what we were talking about earlier, we would not want to kind of round or anything like that. And plus is closer to 2.7. That's really nowhere near it. That is too many. So just like 2 less of figures is not right, too many numbers is not correct either, because it tells people, as we talked about last time, that your measurement is much better than it should be based on that equipment. Obviously, this is correct, but uncertainty wise, that is how far you can take the reading, as it really tells you, as we talked about, you can take it to 2 decimal places. That's where you could take it. This would basically be telling you could take it technically to 3 decimal places, which you cannot on the scale. Any questions on that there? Yeah.
So the number of uncertainty tells you how far you.
Yeah, so as we talked about last time, if you for sure can figure out when you look at a scale how what the smallest markings represent, all you have to do is divide that by 2, and it'll basically tell you how far you can take the reading too. The general rule, if you don't want to have to worry about that, the general rule usually is if you could figure out what the smallest marking is, the general rule is you could usually go one more place to the right of the smallest marking. Not in all cases, like we did an example last time where the smallest marking was 2 milliliters. In that case, you can't go one more place to the right. You could actually only take it to the whole number there, the 1 milliliter and stuff like that. But 99% of the time, you can kind of go one more place to the right of the smallest marking. But again, not 100% of the time. So if you're not sure, that's what you should do. Divide the smallest marking by 2, and whatever you get here is how far you should take the reading to the proper questions. So let's take a look at this one here. Why don't you give this one a go, see what you come up with. Once again, the big numbers go. Okay, so once again here, we're going to look at the scales. So big number, that again means my large marking is 1 centimeter. If we count up the smallest marking starting there and ending here, we once again have 10 markings between those if we do it. And again, if you're not sure, just divide that by 10, gives you a small marking, in this case of 0.1 centimeters. So in this case, this first guy right here would be 9.1, and that's really as far as we need to go because our marking, our arrow is kind of like right there. So that is clearly right after the 9 in this case. It's not really the 9.1. So 9 in this case would be what we would want to record here. Now, obviously, that's 9.1. So clearly, if I recorded, for example, 9.0, that would have how many significant figures? I have 2. The uncertain number here would be the uncertain number actually would be the 0 in this case. And that would be not what we could do here. And again, if you're not sure what we could do here, all you have to do is take this and divide it by 2. And that's going to give you 0.05 centimeters, right? Plus or minus. That means really we should take the reading to 2 decimal places. So in this case, the best choice here out of our list would be the 9.02 centimeters plus or minus 0.05 centimeters, as that is only 2 significant figures. This guy would actually only be 1 significant figure, right? Which is clearly not what it is, because that means I think it's 9, but it could be like 8 or 10. This guy actually is a case of what we were talking about a second ago. It actually has too many digits, right? This is actually correct, but this guy has too many digits. This is telling us we could actually take it to the 3rd decimal place, which is a much better measurement. But based on this scale, we can't do that. We can't go that far. So again, a case of extra digits not good either. So it should be this guy right there. Any questions on that? Yeah. Are you talking about this too? Yeah, so basically to figure out, for example, the kind of plus or minus, or how far you can take the reading to tolerance. Sometimes people call it the uncertainty. Sometimes people call it the precision. Sometimes people call it in the measurement. You can take the smallest digit, the smallest markings, and divide it by 2. And that's how you get to sort of the plus or minus part of that. And what that also tells you is when you get that plus or minus after you divide by 2, that is how far you could take the reading to. So 0.05 is 2 decimal places. So the actual measurement should be taken to 2 decimal places, which the 9.02 would have actually 3 significant figures. The uncertainty here is actually the 2 in this case at the end. It's the uncertainty. Any questions or the estimate? Yeah.
Well, we always divide by 2. Is there any case where we?
No, so to sort of figure out the plus or minus, you always want to divide basically the smallest marking by 2. And again, like I said, you could kind of always, most of the cases, but not 100% of the time, but pretty close to it. Most of the time, you could kind of just go one more place to the right of the smallest marking, which is essentially what this is, right? So the smallest marking is 0.1. We could go one more place to the right, basically in our measurement. So instead of here, we could actually end up there and stuff like that. But if you want to know for sure, all you have to do is just divide by 2. That smallest marking will get you that. Other questions? All right, so as we talked about before, when we take a measurement here, we want to measure from the meniscus. So why don't you take a reading of this one, what you got going on that one? All right, so taking a look at this graduated cylinder, we fill from the top and it pours out the top. So the volume reading increases as you go from the bottom to the top. So we just take a look here, large marking 30, next large marking is 40. So our large markings here are gonna be 10 milliliters in this particular case. If we count up our markings there between those, the smaller markings, we again would start around here. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 markings as we go up that way. So we got 10 markings, tells us that each of the small markings there is going to be 1 milliliter. Now, when we read the bottom of the meniscus, right, we want to go about there. So each of these here, that would be, I'll go inside here, 31, 32, 33, 34, 35. That would be 36, and right about there would be 37 past the bottom of our meniscus. So clearly here, our certain numbers should be 36, right? And now again, if you're not sure really how far you should take the reading to, in this case, all you simply need to do, once again, is divide this by 2, and that will get you 0.5 milliliters, plus or minus. That tells me that I can take the reading here, in this case, to the first decimal place. So clearly, when I look at it, it doesn't look like it's right on the 36. So we would take a reading. I don't know what they did. They might have did, they did 8 in this case. So they felt it was closer to the 37 line than halfway there. So they went with 0.8 and obviously our units. And they added in, again, our plus or minus our uncertainty in this measurement of 0.5 milliliters. Again, the uncertain number here in this case being the 8. Any questions on that? So again, if you're not sure, out the bat, but like it says, sure, that small marking, just divide by 2, and then you'll know for sure how far you should take that reading. Here again, the estimate, when you're trying to do the estimate, it really depends sort of where it falls between the 2 markings. Again, most people, if it's kind of halfway, would put a 5, and then from that point, if it's more than half, you really could pick any number. So sometimes people think when they take a reading, for example, that if they have to go to say point something, that it always has to be a 5. It's always like the number, it's got to be like 36.5. But you should try to estimate, about what it is. So obviously in this case, they feel it was closer to this line. So again, that's why we end up with an 8 here rather than a 5. Same idea if it was closer to this one, kind of similar to the previous example. You wouldn't estimate a 5 there, right? It's kind of closer. Maybe it's a 2 or a 1 or something like that. And so, it doesn't always have to be like a 5 on that last estimated digit. But if somewhere near half between the 2 markings, then obviously 5, but it can be any number really. Yeah.
And then for the large number, you get that 50.
Exactly. So the in terms of the what the large represents the marking, is that what we're talking about, or just what the like
How
this
you would get that number.
the 10 or yeah, so the 10 comes from just taking 2 large markings and subtracting them basically. Yeah. So if you take 40 minus 30, you get 10. Yeah.
If you always subtract them, you'll get that.
You'll get what the large markings represent. Yeah. So in the last one, it was like, for example, 4 centimeters and 5 centimeters. So you take 5 minus 4 is 1 centimeter would be what the large marking represent. Yeah. And then when you figure out how many of the small markings there are between the large markings, then you could divide the large marking by that number, and that'll give you what each small marking represents. So basically, bless you, you subtract the 2 large markings, gives you that number. Figure out how many small markings there are, it gets you that number. Divide them both, gives you what the small marking represents. Divide the small marking by 2, gives you how far you can take the reading to. Yeah. Other questions? All right. Now, a burette is a little bit different. So in a burette, we actually use it for titrations, which we'll use in this class and use a lot in chemistry. Now, a burette's a little bit different. This is a burette. On the bottom, it has like what's referred to as a stopcock. You open it and close it, it lets liquid out. You actually fill a burette from the top. So you put some liquid in at the top, and it comes out the bottom. So when you use something like a burette, the scale is a little bit awkward for a lot of people. It actually increases as you go from the top to the bottom. So at the very top here, that would be 0 milliliters, for example, and then you have like 1 milliliter, 2 milliliters, and so forth. So it actually does increase as you go down. That means, for example, if you're using something like a burette where the scaling increases as you go down, and your volume is somewhere in this area, it is actually 1 point something, not 2 point something. So it increases as you go down, and it's very common people mess it up. It's also very common when people use a burette, for example, if this whole thing was 50 milliliters, it could hold 50 milliliters. A lot of times people record the wrong number up here and they go 50 milliliters because that's what the whole thing could record. You should never do that when you're using a burette. You should always record exactly what the number says on the scale, because when you use it for experiment, you will get the wrong answer if you kind of do that. So with that being said, take a look here and see what you would record for the volume here. And again, remember, it is increasing as you go down. Once again, we're going to look at the large markings. So that's 28 and 29. So if we subtract those two, 29 from 28, we get 1 milliliter as our large markings. If we look here, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So again, we have 10 markings, which means each of our small markings in this case is going to be 0.1 milliliters. So again, it increases as you go down. So this is actually 28.1, 28.2, 28.3, 28.4, 28.5, 28.6, 28.7, 28.8, 28.9, and 29.0. Yeah. So when we look at our meniscus here that I scribbled all over it, right? We could see that it is at least 28.8, which is right around here. So it's at least 28.8. And that would be our certain numbers. Once again, if you're not sure how far you should take this to, you're just going to take the small marking, divide it by 2, and that will get you plus or minus 0.05 milliliters. That tells us we could actually take it to not 1 decimal place, but 2 decimal places in this case. And as you can see there, they feel it's maybe halfway between those 2 markings. So they went with 85 milliliters. And again, the plus or minus 0.05 milliliters. This number would have how many significant figures? That would have 4 significant figures. All these would be significant. All the certain numbers would be these guys. The first uncertain number would be the 5 at the end, which would give you 4 significant figures in this particular case. Any questions on that? So again, you want to look at the scaling. You also want to think about, is it increasing as you go from bottom to top, or is it increasing as you're going from kind of top to bottom? Again, a burette, I would say, is one of the things where you'll see that. Occasionally, a pipette as well, you'll see that. You kind of fill it from the top and you kind of dispense it from the bottom. Pipette, sometimes you see both scales going both directions. They'll kind of go up and down on it. So it kind of depends. But definitely a burette is one we use a lot, and it does increase as you go down. All right. So why don't you take this one here, another burette, different scale perhaps. So see what you would take a proper reading here on this guy. Okay, so let's take a look here again, looking at the big scale there. That is 30, that is 20. So again, if we subtract it, our large marking is going to be 10 milliliters in this case. If we take a look at how many markings we got going on there, that is 1, that is 2, 3, 4, 5, 6, 7, 8, 9, and 10. So we have 10 small markings. Again, if we divide 10 by 10, that gives us that each of the small markings is actually going to be 1 milliliter in this particular case. That would mean that is 21. That guy, right where that thing is at, is 22. And then obviously that would be 23. So we do know in this particular case that 22 should be recorded in this case. That clearly eliminates this guy. That eliminates this guy, right? Now, that gives us a few 22 options that we're looking at here. So we want to make sure that we do record it to the proper digits. So we do know that our small markings is 1 milliliter, right? So we do know that we got 1 milliliter for our small markings. I divide that by 2, 0.5 milliliters plus or minus. That does tell me on this scale, even though it's right on the 22 marking, I have the ability to go one more place to the right of the smallest marking and I should record 22.0 milliliters plus or minus 0.5 milliliters. This would have how many significant figures, this number? Would be 3. The uncertain number here would be the 0, right? Is the uncertain number here. And that would be the proper measurement. Problem with this 22 written this way, it has how many significant figures? Right, the uncertain number here would be the second 2, right? And that's telling you it's like 22, maybe it's 23, maybe it's 21. Again, nowhere kind of near those numbers, so not good. This is, again, that situation we've been talking about, that adding extra zero is not good either, because this number would have how many significant figures? I just circled. Would have 4. The uncertain number would be the last 0, right? And that would basically be saying you could actually make a better measurement than you could with this one, so you cannot. So again, you got to hit it on the right number of digits, no more, no less. Less no good, and more is no good for the same sort of reason. It is not what you should be doing based on that scale. Question. So again, D here should be the right answer. Any questions on taking measurements? So when you take measurements in the lab, you should obviously always take measurements to the proper number of significant figures and digits. And you should perhaps get in the habit of recording the plus or minus. Personally, for me, I don't care all that much about it. But as you go on through other classes here, they care about it. So just try to keep that in mind in lab, kind of record the plus or minuses for anything that is a measurement. That way you're just in a habit doing that as you continue on with other classes here. Don't get in any trouble. All right, so now that we've kind of talked about where significant figures come from, let's talk again about sort of the actual rules for counting something as a significant figure. So the rules for counting significant figures are sort of as follows. Any number that is not a 0 is considered a significant figure. So when we're counting numbers or looking at a number to figure out how many significant figures there are, we are looking to start on the left-hand side, and we start counting when we hit the very first non-zero left to right. So in this case, our very first non-zero is right there at 1, and everything else after that's a non-zero. So this number would have 4 significant figures in this case. Now, zeros, there are a few different types of zeros, and they sometimes give people issues. So the first type of 0 is a leading 0, and those are not significant. So you do not count those. So even though we got some zeros here, zeros here, zeros here, it is not until we get to our first non-zero number that we actually start counting. So because we didn't get to any of the non-zero numbers yet, we don't count any of those zeros. The 4 and the 9 are significant, and this would have 2 significant figures in this case. The next type is a trapped 0, a captive 0, and those are going to be significant. And these are zeros that are between 2 non-zero numbers. So if you have a 0 that's between 2 non-zero numbers, they will be significant. So looking here, this is significant, and that's where we actually start counting. So these zeros here are trapped, so they're going to be significant. And then our 0 at the end is going to be significant as well. So this guy would have 4 significant figures in this particular case. Lastly, here we have the zeros at the end, which are sometimes referred to as trailing zeros. And these are the zeros that really give people a difficult time. So the basic rule is this: when you're counting significant figures and you have zeros at the end, the zeros at the end will become significant if there is a decimal point written in the number. It doesn't have to be near the zeros, it just has to be written somewhere in the number, and that 0 at the end or zeros at the end will be significant. If there is no decimal point written in the actual number, then all the zeros at the end are not significant. This is a situation where you're counting significant figures that you do not assume that there is a decimal point there. So, sometimes we assume, like we're doing scientific notation, that there's like a decimal at the end, and we just kind of assume it's there even though it's not written, and to figure out how many places to do our scientific notation. But in this case, if it is not written, the decimal point, it is not there, it does not count for those zeros. So it has to be actually written in the number. So in this case here, if we had 600 written like this would actually have only one significant figure, starting with the 6. The zeros here are not significant because there is no decimal point written in that number. And again, we don't assume that it's there if it's not written in the case of significant figures. And if we write 600 like this with that decimal point there, it makes these zeros significant. And now you have 3 significant figures in this case. Any questions on that there? So if we had a number like 0.000400032000 centimeters, not sure how you do that, but we'll get some type of measurement like that. And if we want to know how many significant figures would this number have? I have no idea. I was just writing numbers. I don't know. Let's see. So we're going to start here. This is not going to count. This is not going to count. This is not going to count. This is not going to count because those are all leading zeros. The reason they don't count is we have not hit our first non-zero. So we will start counting right there at the 4. We now come across some zeros that are trapped. So those are going to be significant. So significant, 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 non-zero, non-zero. And zeros at the end, are they going to be significant? The answer is yes, because way over here, right, there is that, again, decimal point in this number. It does not have to be right next to them, so it would be significant. So you guys are probably right. 1, 2, 3, 4, 5, 6, 7, 8, 9 significant figures in this particular case. Remember that we also talked about scientific notation the other day, and when you do write a number in scientific notation, all the numbers before the times 10 part are significant. So again, when we have something like this would have 3 significant figures. Again, all the numbers before the times 10 part. Remember, it is how it is written in scientific notation is where the sig figs are, not like after you convert it back to a decimal. So that is that. Again, if we had 1.2 times 10 to the 4, it would have 2 significant figures. So if you have something in scientific notation, whatever number comes before the times 10 part is significant. Any questions on that? Now, significant figures are usually associated with what are referred to, as we'll talk about a little bit later on as well, sort of measured numbers as they come from measurements, as we talked about, and stuff like that. There are certain numbers which are referred to as exact numbers. And exact numbers are one of two things. It's usually a definition, like 12 inches equals 1 foot, something like that. Or it is something that is counted. Like, for example, if I had like 4 apples on the desk, I'm not going to do some type of experiment to figure out how many apples I have on the desk. I'm just going to simply count how many apples I have on the desk. So something that's counted, something that's a definition in chemistry, and we'll talk a little bit more about this when we talk about dimensional analysis. These things are considered exact numbers. And the deal with significant figures and exact numbers is they could have pretty much as many significant figures as you like. So they have as many sig figs as you like. And that's really important, as we'll talk about when we do calculations and we try to get our answer to the proper number of significant figures, because exact numbers can have as many significant figures as you like. We oftentimes will ignore their contribution when they're in a calculation in terms of how far we should take our answer to, because they could vary. Basically, you could have as many as you want. So usually when we're looking at calculations, and we'll talk about and the answer in significant figures, we're looking at really kind of measured numbers and things that have significant figures. We have to take that into account, as our calculation really is only as good as our worst measurement. So our worst measurement is sort of what basically determines how good of a calculation, for example, that we could have. So exact numbers will come across. The good news about exact numbers is they have limitless number of significant figures, and you don't have to worry about them in calculations, but it's really just these sort of measured numbers that you do. Any questions on that? And that's sort of where I was just talking about. So when we talk about exact numbers, again, they are things that are derived, are counted, and these are some of the exact ones that you need to know. So make sure that you know these guys. And here at this school, they sort of consider these things exact numbers. You don't have to worry about 9 pencils, but more so, obviously, this one you should know, this one you should know. Hopefully, you know that one, this one, and this one, these guys. 9 pencils is not necessarily something you should know. All right. So for each of the following, how many significant figures does each of them have? So take a moment and see what you come up with. Let's take a look and see. So once again, here on the first one, going left to right, we're not going to start counting until we hit the 3. And 3 is significant, 0 is trapped, so it's significant, and the 4 is significant. So we should have 3 significant figures there, our last digit. Questions on that one there? This is scientific notation, which means by default, everything before the timestamp part is going to be significant. So this would have 4 significant figures in this case. Here we're going left to right. We're going to start counting up the 1 since it's a non-zero. Everybody else is a non-zero. 3 significant figures. This guy at 10 has 1 significant figure. The 1 is significant. The 0 here is not significant because there's no decimal point written, and it would have 1 significant figure. And lastly, our last one does have 4. Going to start counting here at the 9, and the rest of them will be significant, including this one, because there is a decimal point in the number. So we have 4 significant figures. Now we have 12,000 as how many? As 2. And the uncertain number is which number? It is the 2. Yeah. So that again is the uncertain number. As I was talking about before, this is what I was mentioning. This has 2 significant figures. The uncertain number is the 2. It is not the last number written. Yeah. So last number is written because if we get rid of it, it is no longer 12,000, right? So we want to make sure everything's good. Any questions on sig figs or how to identify it? So let's talk a little bit about rounding. So normal rounding rules do apply. Anything that is 4 or less, we drop sort of the rest of the numbers. And anything kind of 5 and above, we do round up. So we want to make sure we do round correctly. So if I had 13,333 and I want 2 significant figures, what should the answer be? So I heard 13. Anybody else? Okay. How about 13,000? Is there a difference in these numbers? Each has how many significant figures? 2, right? This has 2 significant figures. This has 2 significant figures, right? So in this particular case, the right answer is this one. So let me give you a pretty good example. Let's say I owed you $13,333, and I said, no problem, I'll pay you 2 significant figures. Here's $13. Are you going to take $13 for $13,333? Although it has the right number of significant figures, there is a very big difference in the meaning of the number, right? And you never want to do extreme rounding, which happens a lot because people are so fixed on getting the right sig figs, which is what you should do. But they go like extreme rounding to just get the right sig figs. You never want to change the meaning of the number. 13,000 on the right does have 2 significant figures, and it still maintains really the meaning of the number. 13,333 and 13,000 is pretty good. Maybe I get the $333 teacher discount, right? So it still is about the same amount of money, and it doesn't really change the meaning of it. So it's really important to round to the proper number of significant figures, but it's also really important not to change the actual meaning of the number when you do so in an effort to just get the right number of significant figures. So no extreme rounding, yeah.
So for that first rule, you're not necessarily getting rid of the numbers fully, you're just changing the zeros.
Yeah, you change it to zeros because if you get rid of the numbers fully, you take it to 13, right? And now what you did when you did that is it now means something different, that number, right? And no longer, in the case of the money example, it no longer represents like $13,000 worth of money. You now represents you just have $13 worth of money. So there's a very big difference in the meaning of those two numbers. Even though they both have two significant figures, like I said in my example, you probably wouldn't be happy if I owed you the 13 grand and I just gave you $13 and go like, hey, it's two sig figs, right? You're not going to be really happy with that. It's not, doesn't represent anywhere near what the value should be. So you don't want to change the meaning of the value by rounding. You want to maintain the meaning and you want to maintain the right sig fig. The other thing we could obviously do here as well is we could go scientific notation on this as well, right? So, you know, if we went 1, 2, 3, 4, we could do 1.3 times 10 to the 4. This also would have two significant figures. It also would keep the meaning of it because it's written in scientific notation, because basically when you take that back out is 13,000, right? So it does keep the meaning of it, yeah.
Why wouldn't you just keep that 13,000?
For example, if we were doing some type of calculation and we wanted it to go to two sig figs, which is what we earlier were talking about, that would be why we want to keep it, for example. The only reason, for example, you would keep this at 13,333 is you were doing some type of calculation where you needed 5 significant figures, right? And in terms of significant figures, you might not need that many, but in our example here, we're looking for 2 sig fig. And you know, so we want to make sure we keep the zeros to keep the meaning. You could also do scientific notation. As I mentioned earlier as well, you know, for example, let's just say we did have our 12,000 number before, right? And let's just say we were doing a calculation and we get this on our calculator, but we need 3 significant figures, right? Let's just say that we need 3 significant figures for this answer. The way 12,000 is written, it has, again, how many significant figures? 2. So if I do 120.00, how many significant figures is that? 5. Also, did the meaning just change? It did, right? 120 is very different, right? So that's bad in both accounts. If I go 120 and put a decimal, it has 3 significant figures, but once again, the meaning has changed, right? So we can't do that. We can't put a decimal at the end because we'll now have, again, 5 significant figures, still 12,000 though in that case, but we have too many significant figures, so that would not be good either. So sometimes you'll come across an answer where the only way to get the proper number of significant figures is you need to write it in scientific notation. So this would be an example. If we needed 3 significant figures, there's no way in kind of decimal form that you could get it to the right number of significant figures. So the only way you could do that is you would have to, again, go 1, 2, 3, 4 and write it in scientific notation. Now, again, we do have 3 significant figures and we do have the right meaning to that number. So occasionally you come across that situation where you got to go scientific notation because there's just no other way to get the right number of significant figures and have the right meaning for the number. Any questions on that? Yeah.
I don't understand the second rule.
Yeah. So, for example, let's say we had, let me write one right. Let's say we were going to do, how we could do this, 0.045738, right? Now let's just say we wanted to go to 2 decimal places. Not to, sorry, 2 significant figures was our answer that we wanted. So we want 2 significant figures. Where would 2 significant figures be here? Which number is the second significant figure? Is it the 0, the 4, the 5, the 7, the 3, the 8? Which one is the second significant? It is the 5, right? We're going to go this way. We're going to start counting here. This would be our second significant figure, right? So what the second rule means is we actually always look at the number next to where we want to kind of round, if you will. And in this particular case, the number next to it is a 7. That's above 5, which means we would actually round up. And the proper way would be for this guy, 0.046 would be the right way to do that. We round that 5 up to a 6. Now, if you had this 0.0452, and we also want to go to two significant figures, that would be here. We look at this number. This is actually less than 5. So we just drop these numbers, and we would end up at 0.045 would be the right number. So that's the proper way to round. You always look at the number next to where you want to stop. And then if that one is 5 or above, you round that number up where you want to stop. If it's less than 5, you just drop off the rest of the numbers. Again, making sure you're not changing the meaning of anything along the way.
And that's pretty much what the first row is, right?
Yeah, if it's 4 or less, you drop the rest of them like we would do there on the left-hand side. Yeah. Other questions? Now, speaking of rounding, you definitely do not want to round till kind of the end. So what I mean by that is if you're doing multiple sort of calculations along the way, so for example, if you're going to like get a number here, take that number, do another calculation, get another number, take that number, do another calculation, and so forth. So you're just going to kind of like get an answer, take that number, then multiply it, divide it, whatever, and then do the next operation. You're going to kind of keep doing that. You usually do not want to round to the very end, but you do want to keep track of your significant figures along the way, because every time you round in the intermediate steps of your calculation, you're going to be moving yourself further and further away from the right answer. So it's really important not to round. Some people call it keeping some guard digits, keep a few extra digits along the way if you want to write down the number. Some people will, like, if they're doing a calculation, you know, whatever it may be, they'll keep some extra digits and go, okay, that's kind of where I really should end up, just to kind of keep track of everything along the way in the calculations. You should not round until the very end, but you should keep track of everything and then clean it up at the end. Personally, for me, when I do calculations, I usually just go with the whole numbers in the calculator and just keep rolling with it. But if you want to write down a number in the intermediate step, definitely don't do really hard rounding. If you're going to take that number and do some more calculations with it, take a few extra digits, and usually you don't have to take a ton, but 2-3 extra digits, and usually you're in good shape in terms of any rounding error that you have. So, but if you really strictly round at every step along the way in a multiple step calculation, you will look at the answer and go, wow, that's like nowhere near like where it should be and stuff like that. And it's just kind of rounding error and stuff like that. Any questions? All right, so round each of these to two significant figures and see what it should be. All right, so second significant figure on all these would take us to the 5. Here we would look at the 7, and we do see that it's above 5. So that should get us 36 meters. We want to make sure we include the unit. We'll come here. It is the 8. And here we would look at the 2. That is less than 5, which means basically kind of just turn them into zeros. And in this case, we do need to turn them into zeros to maintain the number of significant figures that we want. If I put a decimal point at the end, would that be good? No, because then I would have 4 significant figures, right? So that would not be so great. We don't want to write 38 either, because that is definitely not the same meaning, right? So although it has the right number of significant figures, it changes the meaning of it. So in this case, we do need to add the zeros to maintain the significant figures. We could also, if you wanted to, do a 3.8 times 10 to the 1, 2, and 3. And that's another way that you could do it. Again, maintaining the number of significant figures in scientific notation if you wanted to. Here, second significant figure takes us to the 6. We're going to look at the 2. In this case, we're going to end up with 0.0026, less than 5. Going to drop it. R. We could also do scientific notation on this one as well. 1, 2, 3. Negative, though, in this case. We go either way there. And lastly here, 2 is our second significant figure. 8 means we're going to round up to 1.3 kilograms in this case. Any questions on any of that there? All right, so let's talk a little bit about calculations and scientific notation and significant figures and calculations. I'll spit that out, right? I think maybe. So when we multiply and divide, we actually look at the number of significant figures. So whichever number in your calculation has the least number of significant figures, that is how many significant figures your answer should have. So if you were going to take 1, 2, 3 times 0.42, this has 3 significant figures. This has 2 significant figures. That means your answer should have 2 significant figures, the least number of significant figures in the measurement, obviously rounded properly to 2 significant figures. If you're dividing, same deal. If you had 0.111 divided by 4.26, this is 4 significant figures. That is 3 significant figures. That means your answer should have the least, which is 3 significant figures. So multiplying or dividing, you're looking at significant figures, it is the least. When you add and subtract, it is actually decimal places that you're looking at, and your answer should have the same as the one with the least number of decimal places. So if you're taking 1.325, you're adding 2.6, and you're adding 3.1111. This has 3 decimal places. This has 1 decimal place. This has 4 decimal places. And if we did that on our calculator here, our display is going to show us 7.0361. So in this case, 1 decimal place is the least. We should go here. This should be 7.0 would be our right answer, our correct answer. This has 1 decimal place. How many significant figures is that? 2, yeah. But 1 decimal place is where it should go based off of this number. As I mentioned earlier, the reason for that is the one with the least sig figs, least decimal places is like your worst measurement, and that's only as good as your calculation can be. If you're doing multiple steps together, you need to keep track of it. So if you're taking 323 times 1.2 divided by 4465, we would do what's in the parentheses first. That is 3 significant figures. That is 2 significant figures. That means when we did the top part of the calculation, we should end up with 2 significant figures. We then are going to divide 2 significant figures by 4 significant figures. That means our answers should end up with 2 significant figures in this case. So if you're doing multiple steps along the way, you should keep track of everything. And again, clean it up at the end in terms of the answer. Any questions on that? All right, we will lay it up there for today.